All right, my 4B geometry class. I know we have kind of taken a step away from our workbook a little bit, and we've been focusing on some SAT type questions, and we've been looking at some data analysis. And so I wanted to just make a quick, hey, watch this and kind of think about some of these properties and some of the different ways that quadrilaterals kind of come up in the world around you, and also in some of the math problems that you may have encountered in the past or will encounter in the future. So I wanted to show you this, this kind of flow chart of these different types of quadrilaterals and just make a quick notation. If it is a four-sided figure, that the sum of the angles is always going to be 360. So sum of the angles in any four-sided figure is going to be equal to 360 degrees. So we knew in a triangle it was 180. In a five-sided figure it turns out to be 540. It kind of goes up by 180 degrees as you increase the number of sides in your polygon. So this is kind of an important little just tidbit of information to kind of pack away. All right. So really I wanted to just show you kind of just this flowchart of how some properties that are true for parallelograms are also true for rectangles and then also for squares. And as you flow down the chart, really what happens is they become more special, right? They have more things that are true about them. They become a little bit less free-flowing in terms of things that are true and not true. Okay, so parallelograms are called parallelograms because opposite sides are parallel. Okay, so that is going to be true for rectangles, squares, and also down this line for your rhombus. So each of these down the flow chart have the same properties of one another, and everything below it has the properties of parallelograms. So we have opposite sides parallel. Opposite sides also happen to be equal. We have opposite angles that are going to be equal in every single one of our parallelograms. And because of this idea of opposite angles being equal, it's also going to be true that our consecutive angles add up to 180 degrees. So in a rectangle, we know that's true because it's 90 and 90. Those are special. This is a little bit more special because of these 90-degree angles, but it is also true in a parallelogram that is not a rectangle or a square, that the consecutive angles are going to add up to 180 degrees. So then you have 180 on either side, and they add up to 360. So that's kind of handy. Over here, the rhombus is a parallelogram. It's not quite a square because it doesn't have 90-degree angles. But what's true about a rhombus and a square, and the reason that they kind of flow one to another, is that they have this property of all sides being equal. So we know that's true for a square. You've dealt with that quite a lot in your math career. But that's also true for a rhombus. Okay. So some of these other quadrilaterals that you see here, trapezoids only have one pair of parallel sides. And those are actually called the bases of your triangle or your trapezoid. And then if you have an isosceles trapezoid, you have one set of parallel lines, and then your other two sides are going to be equal in measure. So it has symmetry. It's an isosceles trapezoid, sort of like you think of an isosceles triangle, but this one is an isosceles trapezoid. So if it is isosceles, you have some extra things happening, like base angles are equal. Those are called base angles right there. And things like that. Okay, and then last but not least, the kite is a little bit of a standalone, and it has consecutive sides that are equal. Not consecutive angles, but consecutive sides. And we will work with, you might have a chance to see some work with the diagonals in the kite and the diagonals in the rhombus in a area formula that's coming up in just a second. Okay, so that's sort of the flow chart for your four-sided figures. Okay. So kind of how does this come into play? Well, in the types of problems that you might be working on in geometry, maybe you have a four-sided figure right here. You don't see anything else labeled, so we don't know if any of the sides are parallel or not, but we do know that these four angles are going to add up to 360 degrees. So for example, on a figure like this, if you were going to solve for x, you would say, well, I know 360 degrees is equal to x plus 2x plus 2x. So I get 360 degrees is equal to 6x. And when you divide by 6, we get 60. So that would mean then that if you were going to come back up, and obviously this is not a picture that is drawn to scale because this would be a 60-degree angle, right? And so with this would be a 60-degree angle. This would be a 120-degree angle. Get my pen to work here. Oops. And also a 120-degree angle here. Okay. And then sometimes you come up across problems that are a little trickier. All right. So here's another example. This time you see we have our x values here, and here. We have our y values right over here. And we still have that kind of unique situation where you are going to have parallel lines cut by a transversal. So really what these are same side interior angles. So I know that 2x plus x has to equal 180 degrees. I also know that, again, parallel lines cut by a transversal. Here are your two same side interior angles. So I also know that 2y plus y has to equal 180 degrees. So I get a value of, this is turning out to be a value we get a lot right now. Dividing by 3 both sides, we get x is equal to 60. And 3y. Dividing by 3 both sides, we get y is equal to 60. And you've solved for x and y in this particular problem. So x is not always equal to 60, but apparently it is for these two problems. All right, the other thing that we've been working on quite a lot right now is making sure that everybody is super comfortable with using the quadratic formula. So I wanted to highlight this problem real quick for you and show you how you could use the quadratic formula to solve. The fact that we know this is a rectangle helps us to know that this side is equal to, this angle at A is equal to 90 degrees, and this angle here at D is also equal to 90 degrees. So I'm going to go ahead and I'm going to add these two expressions together, and I'm going to set them equal to 180 degrees. Okay, so here we go. We're going to say that x squared minus y plus 3x plus y is equal to 180 degrees. One thing that you see happening here with the plus y and the minus y is those two terms are going to cancel. And so I am left with x squared plus 3x is equal to 180. One of the things I want you to have learned during this time that we've been focusing on quadratics is that you always have to set this equal to 0. All right? The goal when you're solving a quadratic is to get either standard form or vertex form or use the quadratic formula. Somehow we need to take a look at solving for this. So we've been working a lot on factoring, so let's go ahead and do that. We're going to subtract 180. So we have x squared plus 3x minus 180 is equal to 0. All right, I don't know if I can move this down, but we'll try. Oh. We'll move it down like this and then move it down a little further. There we go. that worked out just fine. Okay, so let's factor this. We need two numbers that multiply to be negative 180, and we add them together, we get a positive 3. And let's see, I was playing with this, and I think you guys can kind of play with it too. I forget which numbers that we got, 12 and 15. Let's try that. Okay, 12 times 15. They're 3 apart, and when we multiply them together, we get 180. Well, that should work out, because if I use a positive 12, or maybe a negative 12, and a positive 15, then they will be 3 apart, right? They'll add together to be a positive 3, and when I multiply them, I get a negative 180. So again, you guys might be doing some guess and check on your factoring. However you're choosing to factor this, this is going to be x times x. We know we're going to have, to get our positive 3 and our negative 180, we can use negative 12 and a positive 15. To solve, remember we have to bust it into 2 parts. So we have each of these pieces using the zero product property. Add 12 to both sides on this piece, we get x equals 12. Subtract 15 over here, we get x is equal to a negative 15. I think what's going to end up happening is it's possible that that negative 15 may not result in an angle value that is going to work. So once you solve, always remember to kind of take your values of 12 and negative 15 and plug them back in. A lot of times negative numbers don't work when we're looking at a shape, because we want to have a positive angle, or we want to have a positive length of a side. So always when you're solving with quadratics and then applying that to a measurement of some kind, make sure that both your positive and negative versions will give you positive measurements for angles or sides. Okay. So the last thing I just wanted to share with you guys were a couple of formulas right here with quadratics. We are not going to delve into doing a lot of work with these area formulas, but because we might use some of these formulas when we start talking about volume, I did want to show them to you and just remind you that in order to do really good calculations on volume, it kind of starts with being able to find the area of a base. Okay, so if the base of your picture is a circle and the volume of what you're finding is a cylinder, then knowing how to calculate the area of a circle becomes an important part of calculating the volume of a cylinder. Okay, and the same thing is going to be true if the base of anything we talk about is one of these other shapes. So here are just some area formulas, some area formulas that you can look at, kind of refer to. The D1 and D2 in this particular formula refer to diagonal 1 and diagonal 2. So this is a nice little formula. This formula also will work on a rhombus. Okay guys, hope you have a great week. Your assignments this week are going to be dealing with some more data analysis and a little bit more with using your solving quadratics. And we'll keep rolling from there. All right, you're doing a great job. Keep up the good work, and I'll talk to you soon.